Okay, I think this needs some seconds to react. Okay, it's recording now, so maybe let's move on to the second talk of today. So the second speaker today is Jerome. He's from the statistics PhD at Warwick, and he'll be talking about lifetime investment and consumption with Epstein-Zin stochastic differential utility. Okay, Joe, thank you.
Cheers. Thanks for inviting me to talk, Diogo. And cheers, Simon, for the talk before. I really enjoyed that. So I'm going to present on infinite horizon stochastic differential utility. And this is work that I've done with my supervisors, Martin Herdigan and David Hobson. Before I introduce what stochastic differential utility is, I'm going to introduce discounted expected utility. So some of you might have seen this before, but if you haven't, I'll just recap. So the Merton problem, which is essentially an investment consumption problem, I'll describe in a moment, has the goal of trying to maximize the expected value of the following. So this is just the discounted utility of consumption, and U is just concave increasing utility process. So to do this, we're going to introduce the value process, and this VT is essentially just the utility that we get from starting at time t onwards. And so you've got a concrete example in your head. Maybe the most common utility function is this constant relative risk aversion. So if R is less than 1, then it looks something like this. And if R is greater than 1, then everything is negative and it looks something like this. And when R is equal to 1, then it reduces to log utility. So we're trying to maximize this value here. And I guess the first thing to ask is why is that a sensible thing to do? So why don't we just maximize consumption? And essentially, I guess the best way to show this is with an example. So let's suppose you have some wealth X, and I give you the option to flip a coin, right? And if it comes up heads, then I'll double your wealth. And if it comes up tails, then you'll lose everything. So you give me all of your wealth. And I think unless you're slightly reckless with money, you're probably not going to take this gamble. So what economists do to get around this is they say that rational agents prefer the sure thing to the risky thing. So you introduce a utility function, and then you can look at these two things. So here we've got the utility of the expected value of some gamble. So let's call that X. And below, you've got the expected value of the utility of X. And you're always going to have that, the expected value of your utility, the expected value of utility of your gamble is less than or equal to the utility of the expected value. So that's just Jensen's inequality. And if you're thinking about this constant relative risk aversion function, then this R is going to control how big the difference is. So the larger the value of R, the more you're going to need some compensation to actually take this risky gamble. So that is why it's called the coefficient of relative risk aversion. But another thing with this model, and it's possibly slightly less desirable, is, so let's now think about some deterministic C. Deterministic. And so we can get rid of this expectation. We're going to define a new probability measure Q. So Q is just going to be defined on the Borel sets of the positive real line, and it's going to be defined by the following. Right, so this is going to define a probability measure because it's normalized to 1. And because of Jensen's inequality, we can also say that the expected value with respect to Q of U of C, so C is deterministic, and you can think of the sample space of just being your T, is going to be less than or equal to the utility of the expected value of Q. So what this is saying we've got no risk here at all, but this coefficient of relative risk aversion is actually controlling our temporal preferences as well. So This is called a slightly horrible name from the economists, elasticity of intertemporal complementarity. And essentially that is saying that we prefer our consumption to be more spread out, and we don't want to consume in clumps. And for time additive discounted expected utility, R is equal to S. So these two parameters are one and the same. And this is basically too restrictive. So empirically, you don't tend to find that people's risk preferences translate directly into their preferences for temporal consumption. So under stochastic differential utility, we're going to switch out this discounted utility function for something called an aggregator. So this is now allowed to depend on T, C, and importantly, the value process at time T. So we want to define the value process to be the solution to this integral equation. So now it's allowed to depend on all of the values from time T onwards. So you can introduce nonlinearities. But this might not be well defined. So we don't necessarily know that the integral on the right-hand side doesn't have the positive part and the negative part both integrating to infinite values. So we're going to restrict ourselves to some set which we're going to call IG of C, which is just continuous semi-martingales, such that the integral on the right-hand side is actually going to be well defined, and it's going to be finite as well. So we want to find a solution to this. Let's C be a consumption stream, G be an aggregator. We're going to say that V, which is in this integrable set, is a utility process associated to the pair if it's a solution to SDU. And we're going to say that if C has a utility process associated to it, then it's going to be called evaluable. And we're going to denote that set by script E of G. And similarly, if it's got a unique utility process associated to it, then we're going to say it is uniquely evaluable. And so obviously the uniquely evaluable consumption streams are going to be some subset of the evaluable consumption streams. And then we're also going to assume that these are some set of the non-negative progressively measurable processes. And essentially the measurability condition is just the minimal one we want. And we want them to be non-negative because, I mean, economically negative consumption doesn't actually have a meaning. So this presents us with, well, two issues, right? So the first is if we don't have equality here, then there are some consumption streams that we can't actually define stochastic differential utility for. And also, if we don't have equality here, then there are consumption streams which have multiple utility processes associated to them. So these are both issues, and we'll talk about these a bit later. And so we're going to say that the stochastic differential utility associated to a consumption stream is just going to be given by V naught, where V satisfies the previous BSGE. So the investment consumption problem for some aggregator G is for some set of attainable consumption streams. So this is essentially means that they can be financed from some financial market we're going to model, some set of processes which we can actually assign a utility to. So maybe this is the uniquely evaluable consumption streams, but maybe it's a bit larger. So we want to find the supremum over the intersection of these two sets of V naught C. So the constant relative risk aversion utility fits into this framework with the aggregator given by the following. And Epstein-Zin stochastic differential utility is just a generalization of that. So it looks a bit more ugly, but it has quite nice properties. So if S is equal to R, so that was the case I described at the beginning, so the risk aversion and the EIC are equal, then you can see that rho is going to be equal to 0. And so this term is going to disappear, and these are going to be R's. So we are actually going to have the same form. And so we're going to define Epstein-Zin SDU process just to be the solution to this. So I'm just going to briefly introduce the investment consumption problem. We have a financial market with a riskless asset with interest rate R. We got a risky asset, which is just given by geometric Brownian motion with drift mu volatility sigma. And an agent with some initial wealth X has to choose an investment consumption strategy. So pi t just invests is the amount that the agent invests in the risky asset as a proportion of their wealth at time t, and ct is going to be the rate of consumption at time t. And the self-financing condition is the following: we invest 1 minus pi times our wealth in the riskless asset, we invest pi times our wealth in the risky asset, and we consume at a rate ct. And we're going to say that a investment consumption strategy is admissible if the wealth given by the following with initial condition X stays non-negative. So that's just saying we can't go bankrupt. And we're going to say that a consumption stream is attainable if there's some investment process which finances it. So the pair is admissible. So now what we want to do is we want to find the supremum over the attainable strategies of V0 of C. And we've dropped this integrability condition for the moment because this is just a heuristic derivation of the optimal strategy. So 2 ways we can do this. We can first assume that we invest some constant proportion of our wealth into the risky asset. So that's given by little pi. We consume some constant proportion of our wealth, and then we find that the wealth is given by geometric Brownian motion. We can plug that all into the equation and just solve it explicitly. And then we just maximize for pi and psi. Another way we can do it is we just formulate the Hamilton-Jacobi-Bellman equation. So this is pretty standard in control literature. And we just solve that, find the value function and the candidate optimal strategy. So I'm not going to do that, but essentially they give you the same answer, which is promising. And provided this constant eta is positive, the optimal strategy is given by the following, or at least it's the candidate at the moment because we haven't proved it's optimal. So what this eta is saying that essentially delta needs to be big enough, our discount factor needs to be big enough such that the integral actually converges. And so here lambda is equal to the returns of the risky asset minus the risk-free rate over the volatility of the risky asset. So this is called the Sharpe ratio, or the market price of risk in the finance literature. So we're going to invest some constant fraction in our in the risky asset. We're going to consume eta, the same amount as a proportion of our wealth, and then the value function is just given by the following. And we don't need to worry about the value function because it's not that important for this talk. So we've only solved the Hamilton-Jacobi-Bellman equation, which is actually it gives us a candidate, but it doesn't prove optimality unless we've got much stronger conditions. So we're going to prove that now. So we're going to say we need to introduce these notions of a supersolution and a subsolution. So we're going to say that a Cadillac adapted process W is a supersolution if the negative part is uniformly integrable, and if this inequality here is satisfied, and we have a transversality condition as well. But the important part is this inequality, right? So if this were replaced with equality, then W would actually be a utility process. So it's sort of saying in some sense it is above a utility process, and that's what we're going to show. Similarly, a subsolution is similar, but we're going to have that the positive part is uniformly integrable. This is going to be replaced by a less than or equal to, and the transversality condition is going to become lim sup of the expectation of Wt is less than or equal to 0. So you've got this sort of symmetry going on. And this is probably pretty familiar with anyone who has knowledge of BSDEs. And what you tend to do is you just tend to show that a supersolution is going to be greater than or equal to a subsolution, and that's exactly what we're going to do now. So we're going to introduce a couple of conditions on our aggregator, so that the first one is it's increasing in C. which is a pretty standard assumption in economics. It essentially means that more consumption is preferred to less consumption. And then the second is that G is decreasing in V. So this is less intuitive. And for Epstein-Zin stochastic differential utility, it corresponds to rho being negative. So rho has to be less than 1, but it rules out the case rho in 0, 1. And so we can't deal with that at the moment. So basically, the comparison theorem says that subsolutions are always going to be less than or equal to supersolutions. And I'll just give a quick sketch of how the proof of this goes. So suppose that there is some time t such that W1 is actually strictly greater than W2, and then let tau be the first time that that doesn't hold. So that's the stopping time. And then using the definition of sub and supersolutions, we actually get this inequality here. So this is essentially what happens if you plug in the definitions. By the definition of tau, this first one here is going to be less than or equal to 0. Similarly, W1 is going to be greater than or equal to W2 for all s between t and tau, because we haven't hit this stopping time yet, and it's CAD lag. So that means that this term here is also going to be less than or equal to 0, and then so you end up with a contradiction, right? This is less than or equal to 0, but we've assumed it's greater than 0. So a couple of consequences of this, we'll consider the Epstein-Zin aggregator with rho less than 0. So we've got this decreasing in V condition. And the first is that all evaluable strategies are uniquely evaluable. And you can see this by the fact that a utility process is both a subsolution and a supersolution. So you use the comparison theorem twice, you assume you have two, and you find that they're actually equal to each other. The second is that utility processes are increasing in C. So this is, again, like a nice property that we want. So now we need to show existence, because at the moment we don't actually know anything about whether these objects exist. So we could just be optimizing over the empty set, and obviously that is not something we want to do. So this is our Epstein-Zin aggregator, and we're going to define this operator f subscript c. And you see that f is a utility process if and only if it's a fixed point of this aggregator, right? So if and only if vt is equal to f of c vt for all times t. And then similarly, c is going to be evaluable if this operator has a fixed point. So the first thing that we prove is that if C is bounded above by some constant multiple of our candidate optimal strategy, which is just a geometric Brownian motion in this case, then this operator has a fixed point. And so that means that C is evaluable. So that's really nice. And essentially the proof is we map it into a slightly nicer space, and then you show that the operator in that space becomes a contraction and is also a Banach space, so you can just use Banach fixed point theorem. But this is still kind of restrictive, right? So we don't really want to just consider consumption streams that are only bounded above by our optimal or our candidate optimal strategy. So we're going to try and generalize this. So we've got this aggregator which is increasing in C, decreasing in V, and we're going to let script E of G just be the monotone limits of evaluable processes. So for each Cn in that's evaluable, we're going to let Vn be the utility process associated to it, and then we're going to define V to be this limit, which we know it exists because we've showed that Vn is actually monotone in N. So we prove this theorem. So V actually exists, it's unique, and it's independent of the approximating sequence. So that means that if we have, so Cn, we have got some C which is in this set bar E of G, and we've got some sequence that approximates it of evaluable strategies. It means we can take any other sequence of evaluable strategies that converges to it, and they don't necessarily need to be equal, and we get the same value for V. So this is sort of saying that this is a sensible thing to use as a utility process. So we're going to call this object here the generalized utility process. And what you find is actually in the positive case, when everything's positive, this ends up being the minimal supersolution. In the negative case, it ends up being the maximal subsolution. So it's got nice properties as well. So a corollary of that theorem is that we can define a generalized utility process to any non-negative progressively measurable process, which is really nice, because that means we can now consider the problem we actually want to consider, which is that of maximizing over just the attainable consumption stream. So we don't have any integrability condition, which is essentially to make the maths go through. So now we're going to prove the we're going to prove the verification theorem. So that says for a rational agent, so if R and S, the risk aversion and this temporal variance aversion, are positive, if eta is positive and if rho is negative, then the problem is actually the value of the problem is given by V hat of your initial wealth. And the optimal investment consumption strategy is actually this candidate that we found by solving the HJB equation. And we actually show that this condition eta positive is minimal. So if eta is less than or equal to 0, then you end up having for R less than 1, then we can actually find a number of strategies which give us plus positive infinite utility. So it's not a well-defined problem. And if R is greater than 1, then the value of the problem is equal to negative infinite utility for all consumption streams. So that's a nice if and only if condition. So I just quickly breeze through a sketch of that proof. So the first thing to do is show that the candidate value function satisfies the HJB equation. Obviously, if we derived it from the HJB equation, we can miss out that step. Then we're going to apply Ito's lemma to the candidate value function of wealth, and we find that actually the candidate value of wealth is a supersolution associated to the pair FC. So that means by the comparison theorem, we have V hat of X is greater than or equal to V naught of C. So this is the comparison theorem applied at time 0. And then you can also show that under our candidate optimal strategy, because it's got an explicit form, we have equality. So we have equality from number 5. We take the supremum in number 4 and we get this. And then we just use that C star is actually attainable to get this. And that gives us equality of the problems. So a couple more things we'd like to consider is the case rho in 0, 1. So this is interesting because you actually end up having multiple solutions to the SDU equation. So you need to think about which is actually the correct solution and how you can justify that. Finite time horizon existence hopefully will just follow from our infinite horizon existence pretty simply. And at the moment there aren't that many results in the literature, and they impose quite strict conditions. So hopefully we'll be able to just make that a little bit better. And then also we want to generalize the market. So maybe consider a non-Markovian financial market or introduce transaction costs or something like that. So thanks a lot for that. I know it's short on time, but I'll stay around at the end if anyone wants to ask questions.
Okay, before I stop the recording, let's... Oh, I can hear myself. That's okay. Let's get a round of applause for Joe. Yeah. Right, now I stop recording.